Okay, so yesterday's class we quickly saw the, started off looking at the bipolar op-amp, which is the 741. So the primary problem was you have the NPN, which is vertical, which is faster and has larger gain, versus the PNP, which is much slower as well as has much smaller beta. Okay, so you need to design an op-amp with this. Why do you have something like this? Because of the cost of the process. You want to keep the cost down. Why is that? Because this is a general purpose op-amp. Okay, you're going to sell this in millions of parts, so you want to keep the cost down. Okay, so fundamentally you don't want to use a more expensive process, and you want to try to use design techniques to probably minimize the use of the PNP and so on. So we'll look at the exact structure. Okay. So fundamentally the bipolar itself is actually a lateral device, right? So you have the current flowing horizontally, and there is one more thing you can do to actually keep the device, make the device much better for the bipolar. So let us say this is emitter. So I'm looking at the top view. Okay. So the case we saw yesterday was a case where you had one collector, one emitter, and you have current flowing laterally. Now what you can do is you can make the emitter completely surrounded by the collector on all four sides from the top view. That will make it a lot better. So if let us say I make this as my collector. Okay, so which means lateral current flowing in all directions is actually captured by the collector. Right, this is the top view of the device. So current is still flowing horizontally. So the electrons so in this case it's a PNP, right? So the current is actually flowing from your emitter to collector, and you actually capture currents going in all directions. The only current you don't capture is the vertical current. Correct? So you vastly improve your beta. Is that clear? Okay. Now the other thing you can do, which we'll see a little bit later, is you can do, for example, you can separate out this guy only and make the rest of. So what will you get? On one side you will get 1/4 the current, the other side you will get 3/4 the current. You can do things like this. You can have a multi-collector transistor, single emitter, multi-collector. Okay. So you can bias two different circuits, for example. If you want to bias them using just proportional currents, you can do this. Okay. You'll see this. So we'll start looking at the op-amp stage by stage, and you'll see in one of the stages it uses something like this. So this is an example of a donut layout. Okay, so this gives you larger beta. Okay. Okay. So fundamentally, what do you need from the op-amp? So everybody got that? So what do you need from the op-amp? Of course, so you know that fundamentally this kind of op-amp happens to be internally compensated. Okay, unity gain compensated. So you want to make sure it can be used in in any condition, okay, with no stability problems. You want the circuit to be relatively simple. You want it to use less area. So these are all standard things. Okay, nothing special. Now because it's a general purpose op-amp, you want it to have a very large gain. Okay, so that your DC error is small and so on, right? You want it to have very good common mode ranges. So these are all standard things. We have seen the very similar things in the case of the MOSFET op-amp also. Okay, so nothing different about it. And one more thing, what do you need from the circuit itself? you need things like differential to single-ended, same old stuff. Right? In this case, the advantage is, it's a general purpose op-amp, you happen to have dual supplies. So which means it runs off plus or minus 15 volts supply. Okay? And specific to the bipolar itself, in the MOSFET case, you didn't have a problem with input resistance of the op-amp. In this particular case, the bipolar, does take an input base current. You want to reduce it as much as possible. Okay? So you're going to try to increase the input resistance. Okay? And reduce IN, in other words. Okay, this is something special you have to do in this case. So the way you're going to do is very similar to the case of the MOSFET, right? You'll start off with, you can see at least half the concerns are very similar. Okay? Differential to single-ended. So you want some gain from the first stage. Why do you want that? Because if you have, noise, offsets in the second and subsequent stages, they'll get divided down by the gain of the first stage. Right? So you want to have some gain in the, in the early stages. You'll probably have more gain somewhere in the middle. In this particular case, this happens to be a 3-stage op-amp. Okay? Because you're going to use it in general purpose, you want actually very low output impedances also, because you want to be able to drive very, large loads. Okay? So your output impedance needs to be extremely small. So that is one other difference. But you'll see the circuit will be very similar, okay, except for some details, circuit will be very similar. So what we'll do is, to evolve the circuit, we'll start off with something, as close as possible to the MOSFET case. And then we'll start modifying it little by little to improve it. So what we'll do is, to start off with, let's start off with our, what did we do for the MOSFET case? What kind of input stage did we have? We have an NMOS differential pair with an active current mirror load. Let's try the same thing here, right? Why don't we try the same thing here? This is some VB, this is probably a current mirror, okay? So I'm going to call this node X. So you have some current I bias. We'll call this Q5. Okay? So similar to this, right? Q3 and Q4 perform differential to single-ended, right? Just like in the case with the MOSFETs, they do the same function. Okay? But there is one critical difference. Now one problem is, remember, to reach the signal actually does propagate through the current mirror. And we already know that the PNP has low beta, low gain, low speed. Right? So this is not a very good design. You want to keep the PNPs away from the signal path as much as possible, especially in a common emitter configuration. Okay? So you typically don't want to have the base capacitance appearing in the signal path, right? We saw yesterday that there is some base capacitance which can be quite large. In this case, it's not CGS, it's CB, right? Did we look at this? I think maybe I just mentioned it, huh? In this case, because your base width is much larger, you have a much larger transit time, so your effective base charging capacitance CB is much larger. Okay? So you're going to try to keep the PNPs out of the signal path as much as possible, at least in common emitter kind of configuration. We'll see what else can be done. Okay, we'll see if we can use it in a slightly different configuration. Okay, because what you're basically doing is your base capacitance is directly appearing in the signal path. Okay. So your next thing, what will you do? So okay, so suppose you had to modify this. What will you try to do then? You want to keep the PNPs out of the way. So you basically need to first of all need to remove the PNP mirror. Okay, that is one thing you have to do. Okay, what else? Of course, the minute you remove the PNP mirror, you can no longer use this kind of input stage. You can't use a common emitter kind of input stage. So the next stage is to, so I'm going to move my bias to the top side. I'm going to convert my input stages to source follower type stages. Okay. So now I can actually use an NPN mirror. Right? This will work fine. So what you have accomplished is all the devices in the signal path are NPN. Okay, but there is one fundamental problem. Actually there are two of them. One is gain. Okay, gain is obviously very low. The minute you go to source follower kind of configuration, gain is very low. Right? What else? How about the input common mode range? Your input common mode range, you have a VBE here and you have another VBE here. Right? So you almost have no input common mode range at all. Right? You have two VBEs. That's it. Because remember, in the case of a bipolar, it's actually an exponential device. The VBE common mode is always somewhere around 0.7. Right? Okay. So this is the problem with this stage. So now what we are going to do is, so it's around, it's always stuck at around 1.4 volts. Right? Okay. So now what we are going to do is modify this further. But this thing works out because it at least solved our earlier problem. It removed some problems. Now you want to, fundamental thing you want to do is you want to, let's start off with boosting the gain. What can you do to boost the gain? Sorry? So that is one thing you can do. But suppose you want to have some gain in the first stage itself. So what you're going to do is, you're actually going to add a PNP, but in a common base configuration. So it's going to look something like a Cascode. Okay? There is one more advantage to doing that. Okay. Okay. Yes. Yes. What is V in 1? What is V in 1 common mode? What can it be? It has to be VB3 plus VB1. It cannot move from that actually a lot. Even if your supplies are much larger, 15 volts, your input V in 1 has to be always stuck at VB1 plus VB3, which is 1.4 volts. Okay? So you can't do anything about that. VCC. So let us say I set the base of the PNPs to VB2. Now what is the output impedance? What is the gain? It's no longer low, right? Because now your output impedance is actually quite high. High enough such that you can get some gain, right? Okay. Now you have still not solved the common mode problem. What is the common mode of this guy? What is the input common mode? That's it. So it's still not VB2 plus VB5, well, VEB5 plus VBE1. Can this change? No, it can't. Right? The minute you fix VB2, input common mode is also fixed. Is that right? Okay. So what you need is something. So obviously if you fix VB2, input common mode cannot change. So what you need is to devise a scheme to make VB2 float. Okay, change with input common mode. That's what you want. Right? Because you know that your VB2 is always going to be 2 VBs below 1.4 volts below the input common mode. So if you want input common mode to move, you want VB2 also to move. Okay. So what you are going to do is, so you are going to use what is called an indirect biasing scheme. Okay. Let's take a look at that. So I'm going to copy this. Okay, this particular picture. I know you people cannot do that, but I'll just do it because it's a little bit faster. Oh, sorry, this guy. So now you need to fix this VB2. So what I'm going to do is, this is basically just a current source, okay, so don't worry about this, but I'm going to take this. This is your VB. Okay, I'm going to bias it this way. If I do this, if my input common mode, if your input common mode reduces, this point can also fall. Okay. The other thing we'll just see in a moment, maybe in today's class, maybe in next class, we'll see, what the other advantage of doing this is. There is one more advantage as far as the bias currents are concerned. Okay, so we'll look at that a little bit later. But now your VB2 can float, and this happens to be a case of negative feedback. You can actually go through the loop and find out what happens. You can, for example, find out what happens if VB tends to increase. Go around the loop, see what happens, what it does. Okay. I'll leave that as an exercise for you. But this is a case of negative feedback. Okay. Okay. So now you have added the feedback loop, and what you'll have is, let me call this number these again. So Q6, Q7, Q8. Okay. So what you'll find is I7 equals I8 equals I1 approximately. Okay, this is what it's going to do. You have a current mirror here. Let's say this is I1. Sorry, not when I should be careful. Maybe I should call it IA. Okay. If this current is IA, it will make these currents approximately equal. There will be some, some errors because of betas of the PNP and so on. But overall, it will move towards making that happen. Yes. Yes. So in this particular case, what you're doing is, in both cases, you're actually just using the PNP in a common base configuration. You get one more advantage because of using, I think we didn't discuss this, maybe we should have discussed it earlier. One more advantage of using Q5 and Q6 like this is that your input resistance increases. What happens if you have a resistance at the emitter? What does it look like at the base? 1 plus beta times. Right? So you're also improving the input resistance. Okay? So if you have a resistance, if you have a transistor with a resistance on the emitter, from the input, it actually looks larger, 1 plus beta times the resistance at the base. Okay? Yes.
When you connect the connectors together,
yes.
Q1 and Q2, does it work in the same way as the differential pair?
Yeah, you can still, well, apart from this, the two sides are almost similar, right? It's still symmetric.
Yeah, well, so, my point is...
yes, this will still be what looks like a virtual ground. Yes, that point will still look like a virtual ground, right?
Yeah, but the current is depending on the base emitter voltage, right?
Yes. Okay, so what's the difference in the base emitter voltages here? Nothing.
Yeah, but that's because it's not
Yeah, of course, right? If you have, okay, let's say you're trying to pump a current here, some current, right? What is going to happen? That current is going to split equally, because the only impedance difference is actually at the collectors, which is, right? Which is, which is not transparent, which is opaque to what you see at the base or the emitter, right? Assuming that output impedances are large, I'm already assuming that. Okay. What kind of asymmetry? Well, I think any circuit is symmetric to more sensitive to asymmetry. So what makes this particularly more sensitive to asymmetry?
The current through each of the transistors is more sensitive to the emitter voltage than
more sensitive to the emitter voltage here than the collector voltage. Okay, so what's...
suppose I have the differential pair, the normal differential pair.
Okay.
You fix the emitter voltages to be same.
Actually, you don't. If there is mismatch between them, it will never be equal, right? Right. The minute you have mismatches, in the case of a differential pair, also the common emitter is not a virtual ground, because the two sides are not symmetrical. Isn't that right? You will have this one is not that different. It just happens to be a common, source follower instead of a common source, but emitter follower instead of a, differential pair common emitter. That's all. Okay. Okay. So what else can you do to improve the gain? So we have taken care of the upper side. What can you do with the lower side? Yes, I thought I heard somebody say the... Okay, you can do cascode. Cascode is one thing. Anything simpler than a cascode to improve the output impedance? I have a current mirror. Okay. I want to increase the output impedance. What all methods do you know to increase the output impedance? Right? You can degenerate. You can add degeneration resistors here to improve the output impedance. Correct? Okay. What else do you need to do? We have looked at bipolar current mirrors, right? A while back, but we have looked at it. What is the difference between bipolar current mirror and MOS current mirror? Is the base current. So what else do you do? What do you do to take care of the base current? Use a beta helper, right? Okay, so you can put in a beta helper here, right? You can do that. And now that beta helper also needs to be biased. It cannot be biased at the base current. So you need to add an extra biasing circuit also. So we'll look at that. Okay. Now, adding the degeneration resistance. So increases R out. What else does it do? What happens to the mismatch? Did you do that homework where I said you were asked to calculate the mismatch? Right? So it actually reduces. Everybody remembers that? Okay. It improves matching in the current mirror. Okay. Okay. Oops. Let us go back to this guy. I'm going to call these guys X1 and X2, Y1 and Y2. Okay. Where are Y1 and Y2? If you look at the common mode, where are they? It's just V in minus VB, right? The common mode is close to V in at Y1 and Y2. At X1 and X2, where is the common mode? Where is the common mode voltage? So I'm going to call this V. This is your negative supply. It's VEE plus VB3, right? So that means what your the other thing which your PNP pair, right? The PNP common base. The other thing that has done is to actually do a DC level shifting down. Okay, it helps you to do decouple your common mode and shift the DC level down. Okay, so fundamentally you are going to use the PNP in the circuit in two different ways. One is to in the biasing circuit, you want to remove it out of the signal path. Second thing is you have, but even though you remove it completely out of the signal path, you have to use it somewhere because you can't. The NPN, constantly keeps going on in one direction as far as the DC is concerned. Okay, so you need to use the PNP to shift the DC level somewhere. In this particular case, we are using it to shift it from wherever V in 1 is close to the negative supply. Okay. I said something about? No. I said we have decoupled the input common mode from the output common mode of the first stage. That's what I said. Okay. Okay, so now we have enough to come up with the, draw the full input stage. So we have looked at what all we have done. So what have we done? Okay, so we added this, we added the common mode feedback circuit. So this is called a common mode feedback circuit, okay. Now this is also going to be very important for our next topic, which is going to be differential op amps. That will be just a MOSFET case, okay? But this kind of common mode feedback is going to be extremely important, okay? Because in that case, you have differential inputs, differential outputs. So which means you have to have some kind of common mode feedback, okay? So we have to add the degeneration resistors, we have to add the beta helper, we need to find out how we generate VB3, so we need to generate some reference current, right? We need to do all of that, so we'll see how to do all of that. So let's start off with we have the two rails here. So first I'm going to generate so this, I'll call this R5, which is 39 kilo ohms. Okay, so what you'll see is even the values of the resistors and so on are fairly standardized for this 741. Then what changes from product to product? It's typically the betas of the transistors, the speeds, things like that. Those will depend on the process. Okay. So I got this. Okay, so this is okay. This is your VB. So we have added all the details. So let me see. This is 1 kilo ohm. 1 kilo ohm. This happens to be 50 kilo ohms. So this is R1. This is R2. This is R3. What else am I missing? Okay, so this is now your full circuit. Okay, so I'm going to call this current I1. This current will be Iref. This is your collector IC9. So IA is the bias current going through the input stage, the differential portion. Okay, so we have just taken everything except what have we added here. First of all, we have added this reference branch. Okay, what else? We have added the beta helper, and that's it. Actually, we have added this resistance here. What is this current source? We have seen this before, right? It's a Wheatlar current source. Remember this? You had it in one of the homeworks. Okay, so now we have everything. We can actually do a DC analysis. We can find out what the bias currents are, right? What the DC voltages are, and so on. Correct? That's the first step. And what we'll do is, when doing that, we'll assume that we'll assume a number of things. So first of all, the first thing we're going to assume is, we're going to assume there is some overall feedback around the op amp, which is going to set the output common mode to 0 volts across the overall op amp. This is just the first stage. Okay. So now, then we'll ground the the two bases of the inputs, and then we'll start analyzing what the currents are. That will be your steady state, right? Okay. That is one thing. Right? NP and beta is very large. So we are not going to neglect the beta of the PNP, because it will typically be much smaller. So the NP and beta could be, I don't know, 200, 250, something like that. Whereas the PNP could be much smaller, 40, 50. Right? So you can't neglect the base currents. And finally, we'll assume that all devices are in forward active region. Okay, that is, we always do that, right? For proper operation, that has to happen. Okay, actually this should go above this. So these are the assumptions for DC analysis. Okay, so the first step, what is the first step? Find out IREF. Okay. What is IREF? So this is VCC is 15 volts. VE is minus 15 volts. Right? Right? It's VCC plus VEE. So I'll call this minus VEE. VCC minus plus VEE minus VEB of 12 minus VBE of 11 over R5. We'll assume VBE ons are all 0.7 volts, as we have always done. Okay. So first step, IREF is known. Okay, now you have found out it is 733 microamps. Okay. Okay. So then next step, to go here and calculate I1. Okay. Again, we are going to assume that there is no base current through these NPNs. Now you can write an equation, we are going to assume that means IREF flows through Q11. You need to find out. How do you find this out? How do you find out I1? Yeah, VB11 is VB10 plus I1 R4. Right? So you can find out. So you want to find out I1. Right? you remember this from the Vidlar homework? Some of you are saying yes, some of you are not sure. Okay. So it turns out to be this, right? So VB1 minus VB2 is VT ln I1 by I2. Okay. So you get a transcendental equation. You know IREF, you don't know I1, you know R4 and so on, right? You need to find out I1 from this. You can, I don't know, you can iterate, you can do whatever you want to calculate the value. I'll give you the value. Okay. I1 ends up being 19 microamps. Okay. Okay. So now that you have found out I1, what is the next step? Next step is to find out, finally you want to find out these guys, right? You want to find out IA, IC9, right? Those are the things you want to find out. What is the next step? Okay. You can write KCL at two places. One is here, the other is here. Okay. From those two, you will be able to find out. So in this case, if you do this, you will be able to find out the relation between IC9 and I1, which is 19 microamps. In the other case, you can do the same thing for IA. So let's first write it here. Okay, we are first going to write it at this point. Oh well, actually I should be careful. We are actually going to write it at this point. Okay. So your IA is nothing. Yeah, this is right. Okay. First of all, what is the ratio of IC8 to IC9? Why is that? Well, the collector currents are always the same because the VBEs are the same, right? The collector currents have to be equal. So IC8 is always equal to IC9. Okay. So look at the, also look at the directions I have chosen. I have chosen IC8 flowing upwards, right? Minus IC9. This includes your base current also. Correct? You have IC9, you have 2 over beta times. You have the 2 base currents flowing out also. That gets added, so you have IA. Correct? So this is the first equation you can write. The other thing you are going to assume is, because Q1, Q2 have very large betas, you are going to assume that the collector current is same as the emitter current, for at least for Q1. Okay, and that happens to be the emitter current for Q3 and Q4. Okay. Okay, and what is this? This is the same as IA. Correct? So IA splits into IC1, IC2, becomes IE1, IE2, which is same as IE3 and IE4. Okay. Now you can write, because you can write a KCL here relating this current. That's the base current. That is where the feedback part comes in. No, because and that you can relate to again IC9 and what is known, which is I1. Okay, so in other words, you're trying to calculate, let us say, these currents or something related to these currents in terms of maybe I1 and maybe the betas of the transistors. Okay, what is this? Okay, so now I'm going to do KCL at node X. What is this? What is IC9 plus I1? It's nothing but IB3 plus IB4. Correct? Right? It's just 1 over beta plus 1 times the emitter current, sum of the emitter currents. What is this? We know what I3 plus I4 is based on this equation. So this is what you have. So what is I1? 19 microamps. Okay. Okay. Is that right? I've just taken this IC9 to the other side, that's all I've done, and just grouped the terms for IC9. Okay, so now you know IC9 in terms of, once you know beta P and P for that particular process, for the particular bias current, you already know IC9. Okay, now the next step is to find out what IA is. Okay, because that's what you're trying to find out. IA is, right? So I'll call this 2. I'm going to substitute 2 in 1. I'm going to substitute the expression for IC9 into IA. Okay. So what that will give you is okay, you get something like this. You can keep simplifying it further. What you'll see is you can make certain assumptions. You already know, you can do 1 over 1 plus x is 1 minus x. You can keep making, simplifications like that. Finally, what you'll end up with is you'll end up with this. Okay. Next step, once we have found out IA, so now we have found out IA, Now I'm going to find out these guys, IC3 plus IC4. Okay, what is IC3 plus IC4? It's just IE3 plus IE4 over into beta over beta plus 1. Okay. And what you'll find, this will end up being 19 microamps. Okay. So in other words, what happens is, so fundamentally what is the reason for this? Because you have this common mode feedback here. That's why you are able to write KCL and equate the currents and so on. So what this common mode feedback does, you have an input current of 19 microamps. It makes sure that the bias currents here, IC3 plus IC4, is also fixed at 19 microamps. Okay. Okay, so what we'll do is we'll stop here and continue next class. So what we are going to do is we are going to do the DC, we have pretty much done most of the DC for the first stage. We'll look at the second and third stages. We'll look at, just drawing the whole thing itself will take like 15 minutes, right, for me. So, and I don't know if I can fit it into one of these. So what I'll do is we'll just look at it stage by stage. If you want the whole thing, you can go look at a textbook and you can pick out Gray and Meyer, right? They have it in their book. Okay. So what we'll do is we'll do the DC analysis. After that, we'll do the small signal analysis. We'll find out R in, R out, voltage gain of each stage, so that we can find out the overall DC gain, overall input resistance, output resistance, and so on. Okay. And then we'll finish. That's more than that you don't need to know about the 741. Okay. Okay. See you tomorrow.